Somewhere out in the dark, a dead star is spinning 700 times every second. It is heavier than our sun, yet crushed into a sphere you could drive across in half an hour, and it whirls so fast that its surface is racing around at nearly the speed of light. It has been turning like this for millions of years, and it will keep turning long after our sun has burned out. Nothing pushes it. Nothing winds it back up. It simply spins, because once something in this universe begins to turn, stopping is the hard part. That same stubborn turning is everywhere, hiding in plain sight. It is in the slow wheel of the galaxy overhead, in the orbit of every planet, in the swirl of water vanishing down a drain, and in the particles deep inside your own body. The universe is filled, from edge to edge, and from the largest scales to the smallest, with things that turn, and almost none of them were ever set spinning by anything we would recognize as a push. This is why a question that sounds almost too simple to ask opens a door onto some of the deepest physics we know. Why does everything spin? Why is turning the natural state of nearly everything in existence, while true stillness is almost impossible to find? The answer begins in the collapse of a cold cloud of gas, and from there it reaches into the birth of stars, the shape of worlds, the hearts of black holes, and the architecture of the cosmos itself. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. Start with where you are. You feel motionless. The chair holds you, the floor is steady, the walls do not move. But this stillness is an illusion stitched together by the fact that everything around you is moving along with you. The Earth completes one full turn roughly every 24 hours. At the equator, the surface is traveling at about 1,670 kilometers per hour just to keep up with that rotation. You do not feel it because there is nothing to feel it against. The air spins with you. The oceans spin with you. Your own body has been spinning since the moment you were born. This is the first clue. Rotation, once it begins, does not simply stop. It persists smoothly and silently until something acts to slow it down. And in the near vacuum of space, very little acts to slow anything down. To understand why our planet turns, you have to go back to before the planet existed at all. 4.5 billion years ago, there was no Earth, no sun, no moon. There was only a vast cloud of gas and dust drifting in a quiet arm of the Milky Way. This cloud was enormous, stretching across distances that light itself would take years to cross. It was cold, dark, and almost unimaginably thin. In most places, a single cubic centimeter of that cloud held only a handful of atoms, and yet within that thin, freezing fog lay everything that would one day become our world. The cloud was not perfectly still. Nothing ever is. Tiny currents stirred through it, gentle drifts of gas moving in slightly different directions. Some regions were a little denser than others. Some particles drifted left while their neighbors drifted right. Across the whole cloud, all these little motions mostly canceled out, but they never canceled out perfectly. There was always a faint, leftover tendency for the cloud to circulate, ever so slightly, in one overall direction. This faint, leftover turning is the seed of everything that follows. To see why it matters, we need to understand one of the most important ideas in all of physics, a principle that quietly governs spinning things across the entire universe. It is called the conservation of angular momentum. The name sounds intimidating, but the idea is something you have seen with your own eyes. Picture a figure skater spinning on the ice. She begins her spin with her arms stretched wide, turning at a gentle, graceful pace. Then she pulls her arms in tight against her body. And without pushing off the ice, without any extra effort, she suddenly spins faster. Much faster. She becomes a blur. Then she extends her arms again, and the spin slows back down. She did not add any new turning to her body. She simply changed her shape. When her mass was spread out wide, she turned slowly. When she gathered that mass close to the center, she turned quickly. This is angular momentum in action. In the language of physics, angular momentum is a measure of how much spinning motion an object has, and it depends on three things: how much mass is turning, how fast it is turning, and how far that mass sits from the center of the spin. The crucial fact is that in an isolated system, this quantity is conserved. It cannot simply vanish, and it cannot appear from nothing. If the mass moves closer to the center, the spin must speed up to compensate. If the mass moves outward, the spin must slow down. The total stays the same. Now take that idea and apply it to our enormous cloud of gas, drifting in space with its faint, barely noticeable rotation. For millions of years, nothing dramatic happens. The cloud drifts and turns at its own glacial pace. Then something disturbs it. Perhaps a nearby star reaches the end of its life and detonates, sending a shock wave rippling outward through space. That wave slams into the cloud, squeezing it, pushing parts of it together. In one region, the gas grows just dense enough that its own gravity takes hold. Gravity is patient, and gravity is relentless. Once a clump of gas becomes dense enough to pull on itself, it begins to fall inward. The cloud starts to collapse. And here is where the figure skater returns to the story. As the giant cloud collapses, all that material rushes inward toward a common center. The mass that was once spread across light years begins gathering into a far smaller space. Remember what the skater taught us. When spinning mass moves inward, the spin must speed up. So the cloud, which had been turning so slowly that you could barely call it turning at all, begins to rotate faster and faster. The further it collapses, the quicker it spins. What started as a barely perceptible drift becomes a genuine, churning rotation. The cloud is now a spinning, contracting maelstrom of gas and dust, growing denser and hotter at its core. This is the moment a solar system is born. But the spinning does something remarkable to the shape of the cloud. As it whirls faster, it stops being a shapeless blob and starts to flatten. Think about what happens when a pizza chef spins a ball of dough in the air. The faster it spins, the flatter and wider it gets, stretching out into a disk. The same thing happens to the collapsing cloud, but on a scale beyond imagination. The spinning gas flattens into an enormous rotating disk, with the dense, growing core at its center. Astronomers call this a protoplanetary disk, and it is one of the most beautiful and important structures in the universe. We have actually photographed these disks around other young stars. They appear as glowing rings and spirals of material surrounding a brilliant point of light. Each one is a solar system caught in the act of being born. At the center of our own disk, the gathering material grew so dense and so hot that something extraordinary ignited. When the core reached temperatures of millions of degrees, the atoms there were crushed together so violently that they began to fuse. Nuclear fusion switched on. A star was born. Our sun lit up for the first time, and it inherited the spin of the cloud that made it. To this day, the sun rotates, carrying that ancient angular momentum. It turns roughly once every 25 days at its equator. The same spin that lit the sun also shaped everything that orbits it. Out in the surrounding disk, the leftover gas, dust, and ice were all circling the newborn star in the same direction, because they all inherited the rotation of the parent cloud. Tiny grains of dust drifted through this disk, occasionally bumping into one another. Some of them stuck together. Over time, those clumps grew into pebbles, then boulders, then bodies the size of mountains. These growing worlds swept up more and more material as they orbited, and gradually they became planets. And because they all formed from the same spinning disk, they share a striking family resemblance. Look at our solar system today, and you will see the fingerprint of that original spin everywhere. Nearly all the planets orbit the Sun in the same direction. Most of them also rotate on their own axes in that same direction. And almost all of them lie in roughly the same flat plane, like marbles rolling on a tabletop rather than scattered randomly through a sphere. This is not a coincidence. It is the preserved memory of the disk they were born from. When you look up and see the planets tracing a single line across the night sky, you are seeing the flatness of that ancient disk written into the heavens. The whole solar system is, in a sense, a fossil of a single spinning cloud, yet the planets are not all the same, and their differences tell their own stories about spin. Consider the rotation of the worlds around us. Earth turns once roughly every 24 hours, giving us our familiar day and night. Jupiter, the giant of our solar system, spins astonishingly fast for its size. Despite being large enough to swallow more than 1,000 Earths, it completes a full rotation in less than 10 hours. A day on Jupiter is shorter than a single working shift on Earth. That blistering spin has a visible effect. Jupiter is noticeably squashed, bulging outward at its equator and flattened at its poles, stretched into a slightly oval shape by the force of its own rotation. If you look at a precise image of the planet, you can actually see that it is not a perfect sphere. The same is true, in a gentler way, of Earth. Our planet is very slightly wider around the equator than it is from pole to pole, pushed outward by the steady force of its own turning. The faster a world spins, the more it bulges. Spin shapes worlds. But some planets break the pattern, and those rule breakers are some of the most fascinating objects in the sky. Take Venus. Almost everything in the solar system rotates in the same direction, the leftover spin of the birth cloud. Venus does the opposite. It turns backward, rotating in the reverse direction compared to nearly every other planet. If you could stand on its surface and watch the sun, it would rise in the west and set in the east. Why does Venus break the rule? Astronomers are still working that out. One leading idea is that, long ago, Venus suffered a colossal impact, a collision with another large body that flipped or reversed its spin. Another possibility involves the thick, heavy atmosphere of Venus and the powerful gravitational tug of the Sun, which over vast stretches of time may have dragged its rotation to a near halt and then nudged it into reverse. Whatever the cause, Venus turns with breathtaking slowness. A single rotation takes about 243 Earth days. Strangely, that means a day on Venus lasts longer than its entire year, since Venus circles the Sun in only about 225 Earth days. Then there is Uranus, perhaps the strangest spinner of all. Most planets rotate like spinning tops, more or less upright as they orbit the Sun. Uranus rotates on its side. Its axis is tilted so far over that the planet essentially rolls around the Sun like a ball, with its poles pointing nearly toward and away from the star. The result is the most extreme seasons in the solar system. For about 42 years at a time, one pole of Uranus faces continuous sunlight, bathed in an endless day. Then, as the planet continues its slow orbit, that same pole turns away and endures roughly 42 years of unbroken darkness. Each pole experiences seasons that last for decades. The most likely explanation for this sideways orientation is, once again, violence. Early in its history, Uranus was probably struck by one or more massive bodies, impacts powerful enough to knock the entire planet over and leave it tipped on its side ever since. These exceptions are revealing. They show that while spin is inherited, it can also be altered. A collision can flip a world, a gravitational tug can slow it, a glancing blow can tip it over. The default state is to spin in the direction of the original cloud, but the universe is a chaotic place, full of impacts and tugs and gradual nudges that can rewrite a planet's rotation over billions of years. And spin does not only shape planets, it shapes their futures, and even the rhythm of life upon them. Here on Earth, our spin is not perfectly constant. It is very slowly winding down. The reason hangs in our sky every night. The moon, our constant companion, raises tides in our oceans through its gravitational pull. As Earth rotates beneath those tidal bulges, the water sloshes and drags against the ocean floor and the continents. This dragging acts like a faint, ceaseless brake on our planet's rotation. Bit by bit, century by century, it bleeds away a tiny fraction of our spin. The effect is almost imperceptible on a human timescale. Each day grows longer by only a few thousandths of a second over a century. But over hundreds of millions of years, it adds up dramatically. We have evidence of this written into ancient corals and fossil shells, which grew in daily and yearly layers, much like the rings of a tree. By counting those layers, scientists have discovered something remarkable. Hundreds of millions of years ago, a day on Earth was only about 21 or 22 hours long. The planet spun faster, and the years held far more days, because each day was shorter. The dinosaurs experienced shorter days than we do. And the angular momentum that Earth loses does not simply vanish, because the universe will not allow that. It is transferred to the moon. As Earth's spin slows, the moon is gently pushed into a wider orbit, drifting away from us at a rate of a few centimeters every year, about the speed at which your fingernails grow. The slowing of our spin and the retreat of the moon are two halves of the same cosmic accounting. Angular momentum is being passed from one to the other, never created, never destroyed, only moved. This same process, taken to its extreme, produces one of the most curious arrangements in space. The moon itself once spun much faster than it does now. But over billions of years, Earth's gravity raised its own tides in the solid rock of the moon, slowing its rotation until something locked into place. Today, the moon turns exactly once for every orbit it makes around Earth. The consequence is that the moon always shows us the same face. The far side of the moon is forever hidden from anyone standing on Earth. A hemisphere no human eye saw until spacecraft finally carried cameras around the back. This phenomenon is called tidal locking, and it is everywhere in the universe once you know to look for it. Many of the large moons of Jupiter and Saturn are tidally locked to their planets, always presenting the same face to the world they circle. Given enough time, the same fate may await many planets that orbit close to their stars, eventually turning one side permanently toward the heat and leaving the other in permanent night. Spin, it turns out, is not just a property an object has. It is something that flows between objects, traded back and forth through the invisible grip of gravity, slowly reshaping orbits and days and the very rhythm of worlds. Now, lift your gaze beyond the planets, past the edge of our solar system, and consider the stars themselves. Every star you have ever seen is spinning. Our sun, that enormous ball of glowing plasma, turns on its axis just as the planets do. But the sun is not solid, and this makes its rotation strange. Because it is made of gas and plasma rather than rock, Different parts of it can turn at different speeds. The sun's equator completes a rotation in about 25 days, while regions near its poles take closer to 35 days to come around. The star does not turn as a single rigid body. It rotates in layers, faster in the middle, slower at the top and bottom, a phenomenon called differential rotation. This uneven spinning has dramatic consequences. The sun is threaded through with powerful magnetic fields, and as the differently rotating layers drag those fields around, the fields become twisted, stretched, and tangled. Over time, this tangling winds the magnetic field into knots and loops that burst through the sun's surface. These are the engines behind sunspots, solar flares, and the great eruptions of plasma that occasionally hurl themselves across the solar system. When one of those eruptions sweeps past Earth, it can light up our skies with auroras and, in extreme cases, disrupt our satellites and power grids. The spin of the sun, twisting its magnetic field, is the hidden source of this space weather. Other stars spin far faster than ours, and their rotation can be extreme. Some young, hot stars whirl so quickly that they are visibly flattened, squashed into oval shapes by the sheer speed of their turning. A star named Achernar, one of the brightest in the southern sky, spins so rapidly that it is dramatically wider across its equator than from pole to pole, more like a flattened lens than a sphere. But the most extreme spinners only reveal themselves when a star reaches the end of its life. And here, the story of spin reaches a crescendo. When a massive star runs out of fuel, its core can no longer hold itself up against gravity. In a fraction of a second, that core collapses. A region, perhaps the size of a large city's worth of stellar material, crushes down to something only a few dozen kilometers across. And now, think back to the figure skater one final time. The collapsing core had been spinning, like all stars, at a stately pace. But as it crushes inward, its mass rushes toward the center on a scale almost beyond comprehension. The spin must speed up to conserve angular momentum, so it speeds up enormously. A core that once took weeks to rotate, when squeezed down to a sphere only 20 or so kilometers across, ends up spinning many times every single second. These collapsed stellar cores are called neutron stars, and they are among the most extreme objects in the universe. A neutron star packs more mass than our entire sun into a ball you could drive across in half an hour. A single sugar cube of its material would weigh as much as a mountain, and the fastest of them spin at a rate that defies belief. The quickest known neutron stars rotate over 700 times per second. Pause on that for a moment. An object more massive than the sun, turning 700 times every second, its surface whipping around at a sizable fraction of the speed of light. This is the figure skater principle pushed to its absolute limit, the inherited spin of a star concentrated into a city-sized sphere. Many of these objects also fire out beams of radiation from their magnetic poles. As the neutron star spins, those beams sweep across space like the rotating light of a lighthouse. If one of those beams happens to point toward Earth, we detect a flash, then nothing. Then a flash again, with each rotation. These flashing neutron stars are called pulsars, and they are so regular that some of them keep time more precisely than the finest atomic clocks ever built. A pulsar is, in a very real sense, a cosmic clock, ticking with the rhythm of a dead star's spin. The first one discovered pulsed so steadily that, for a brief and thrilling moment, astronomers wondered whether they had stumbled upon a signal from another civilization. It was not a signal. It was something almost stranger. It was the relentless, perfect spin of a collapsed star, a heartbeat written by physics into the dark. If a collapsing star is even more massive, the core does not stop at the neutron star stage. It keeps collapsing, past every limit, until it forms the strangest object in the cosmos: a black hole. And black holes spin too. In fact, most of them spin ferociously. When a star collapses to form a black hole, that same conservation of angular momentum applies. The spin of the original star is concentrated into the black hole, and because black holes are so compact, that spin can become extraordinarily fast. A spinning black hole is profoundly different from a stationary one. A black hole that does not rotate is, in a sense, simple. It has a center and a boundary, and that is nearly all. But a spinning black hole drags the very fabric of space and time around with it. This is one of the most mind-bending predictions in all of physics, and it has a name: frame dragging. Imagine setting a spinning ball into a thick pool of honey. As the ball turns, it pulls the honey around with it, creating a swirling current near its surface. A spinning black hole does the same thing, except the honey is space itself, and the swirling extends out into the surrounding cosmos. Near a rotating black hole, space and time are caught in this whirlpool, dragged around the hole whether anything wants to be or not. Within a certain region around a spinning black hole, it becomes literally impossible to stand still. No matter how powerful your engines, you would be swept along in the direction of the spin, carried by the rotation of space itself. We have actually measured this effect. Delicate experiments using satellites in orbit around Earth have detected the faint frame dragging caused by our own planet's far gentler spin, confirming that this strange swirling of space is real. Around a black hole, the effect is overwhelming. The spin of a black hole is not a minor detail. It can store a tremendous amount of energy, and under the right conditions, that energy can be unleashed. Some of the most powerful phenomena in the entire universe are believed to draw their energy from the rotation of black holes. At the centers of many galaxies sit supermassive black holes, monsters millions or billions of times more massive than our Sun. When matter spirals toward one of these giants, it does not fall straight in. It forms a swirling, superheated disk, glowing with the heat of friction, circling the black hole at tremendous speed. And from the poles of some of these systems, vast jets of matter and energy blast outward into space, stretching for thousands or even millions of light years. These jets are among the largest single structures in the universe, and the engine driving them is thought to be the spin of the central black hole, twisting magnetic fields and flinging material outward along its axis of rotation. A spinning black hole, in other words, can act like a cosmic dynamo, lighting up an entire galaxy and reaching across intergalactic space. The very brightest objects we can see in the distant universe, brilliant beacons called quasars that outshine entire galaxies, are powered in part by the rotation of these enormous black holes at their hearts. Spin, which began as the faint drift of a gas cloud, ends up among the most powerful forces shaping the visible universe. Zoom out further still, and the spinning does not stop. Our galaxy, the Milky Way, is itself an enormous rotating disk. Hundreds of billions of stars, vast clouds of gas, and immense quantities of dust all wheel together around the galactic center in a slow, majestic turn. Our Sun, carrying Earth and all the planets with it, is one of those orbiting stars riding around the galactic core at roughly 230 kilometers per second. Even at that staggering speed, the galaxy is so vast that the Sun takes around 230 million years to complete a single lap. The last time our solar system was on the opposite side of this orbit, the earliest dinosaurs were just beginning to appear on Earth. We are, all of us, passengers on a turning wheel so large that one rotation spans 250 million years. And just as a spinning cloud flattens into a disk, the Milky Way is flattened too. Seen from the side, it would look like a thin, glowing plate with a bulge in the middle, its stars confined largely to a single plane, exactly as the physics of rotation demands. The graceful spiral arms that decorate galaxies like ours are patterns within this great rotation. Regions where stars and gas pile up more densely, like the slow ripple of a traffic jam wheeling around the galactic center. But the rotation of galaxies hides one of the deepest mysteries in modern science. When astronomers carefully measured how fast the outer parts of galaxies were turning, they found something that should not have been possible. The outer stars were moving far too quickly. Based on all the visible matter, all the stars and gas and dust we can see, the outskirts of galaxies should rotate more slowly than the inner regions, just as the outer planets in our solar system orbit more slowly than the inner ones. Instead, the outer stars were racing around nearly as fast as the inner ones. By every calculation, galaxies spinning that fast should tear themselves apart, flinging their outer stars off into intergalactic space. Something was holding them together, some unseen mass providing extra gravity. This discovery, born from studying how galaxies spin, became one of the strongest pieces of evidence for one of the great enigmas of the cosmos: dark matter. An invisible substance that does not shine, does not block light, and cannot be seen directly, yet appears to outweigh all the ordinary matter in the universe several times over. We cannot see it, but we can feel its effect through the way galaxies rotate. The spin of galaxies, in other words, points to the existence of vast quantities of matter we still do not understand. A simple question about turning leads straight to the edge of human knowledge, and the structures grow larger still. Galaxies gather into clusters, and clusters into superclusters, immense webs of matter spanning hundreds of millions of light years. These too show motion and rotation on scales almost impossible to picture, slow wheeling dances of entire galaxies around their shared centers of gravity. At nearly every level of the cosmos, from moons to planets to stars to galaxies to clusters, the same theme repeats: things turn. So we return to the original question, but now with deeper understanding. Why does everything spin? The answer has two parts, woven together. The first part is that spin is almost impossible to avoid. Picture again that vast cloud of gas before it collapses. For it to end up with absolutely no rotation at all, every single one of its countless drifting motions would have to cancel out perfectly, leaving not even the faintest residual turn. In a cloud spanning light years, stirred by countless currents and disturbances, that perfect cancellation simply never happens. There is always some leftover circulation, however small. Always a faint bias toward turning one way rather than the other. Perfect stillness, in a real and messy universe, is essentially impossible. The dice are loaded toward rotation from the very beginning. The second part is that whatever small spin exists gets amplified, sometimes enormously, when things collapse. This is the gift of the figure skater, the conservation of angular momentum. A barely turning cloud, light years across, contracts down into a star and its planets. And in doing so, its gentle rotation is concentrated and sped up, sometimes into the wild spinning of a young star, sometimes into the dizzying whirl of a neutron star turning hundreds of times each second. The universe takes the faintest hint of rotation and magnifies it through collapse. Together, These two facts explain the pattern. Spin is nearly inevitable because perfect stillness almost never occurs, and spin is dramatically amplified whenever matter gathers itself inward under gravity. That is why rotation is the rule and stillness the exception, from the smallest worlds to the largest galaxies. But there is a final, beautiful layer to this story, and it concerns the universe as a whole. If almost everything within the universe spins, you might naturally ask the ultimate question. Does the entire universe spin? Is the cosmos itself, taken all together, rotating around some grand axis? This is a profound question, and scientists have looked hard for an answer. If the universe as a whole were spinning, it would leave subtle fingerprints on the oldest light in existence, the faint afterglow left over from the birth of the cosmos itself. That ancient light, stretched and cooled over billions of years, fills the whole sky, and it carries within it a record of the early universe. A rotating universe would imprint a particular pattern, a kind of cosmic lopsidedness, onto that light. When scientists examined this ancient glow with extraordinary precision, mapping it across the entire sky, they searched carefully for any sign of such a pattern. For the most part, they found none. As far as our best measurements can tell, the universe on its largest scales is not spinning in any obvious way. It appears to look essentially the same in every direction, with no grand axis of rotation, no overall cosmic whirl. This may seem strange, given that almost everything inside the universe turns. But it fits with the picture we have built. Spin arises locally, wherever clouds of matter collapse and concentrate. Each region inherits its own small rotation, pointing in its own random direction. Across the whole universe, all these countless spins point every which way, and they average out. The galaxy turns one way, a distant galaxy turns another. A third tumbles along a different axis entirely. Add them all together across the vastness of space, and the grand total comes very close to nothing. The universe is full of spinning things, yet the universe as a whole barely spins at all, because all that local turning cancels out on the largest scale. To truly appreciate why spin is so universal, it helps to slow down and look more closely at that very first ingredient, the gentle leftover turning of the cloud. It is tempting to imagine that a cloud needs some special push to start rotating, some cosmic hand to set it spinning. But the truth is the opposite. A cloud needs a special effort to not rotate. Consider what a giant cloud of gas actually is. It is not a tidy, smooth object. It is a turbulent, churning mess, shaped by the chaos of the galaxy around it. Shock waves from exploding stars ripple through it. The gravity of passing stars tugs at one side and then another. The cloud orbits the center of the galaxy, and different parts of it feel slightly different pulls because they sit at slightly different distances from the galactic core. The inner edge of the cloud orbits a little faster than the outer edge, simply because it is closer in. This difference, played out across the whole cloud, gives it a gentle, built-in tendency to shear and circulate. The galaxy itself, by turning, plants the seed of rotation in every cloud that drifts within it. So the spin of a newborn solar system is, in a way, a faint echo of the spin of the entire galaxy passed down through the cloud that gave it birth. And because galaxies spin, and the clouds within them inherit a whisper of that spin, the systems born from those clouds spin in turn. The rotation cascades downward, from the galaxy to the cloud, to the star, to the planets. It is turtles, in a sense, all the way down, but the turtles are spinning. Now think about what conservation of angular momentum really demands. because it is even more dramatic than the figure skater suggests. When that cloud collapses, it does not shrink by a small amount. It shrinks by an enormous factor. A cloud light years across collapses down to form a star roughly the size of our sun, a sphere only about 1,400,000 kilometers wide. That sounds large, but compared to the original cloud, it is almost nothing, like a vast stadium shrinking down to a single grain of sand. When mass falls inward by such a colossal factor, the speeding up of the spin is correspondingly colossal. If the original cloud had retained all of its angular momentum and packed it into the star, that star would be spinning so fast it could not possibly hold itself together. It would fly apart instantly. This presents a genuine puzzle, one that puzzled astronomers for a long time. If the figure skater principle is so powerful, why is our sun spinning so calmly? Why does it take 25 days to turn, rather than spinning itself to pieces in seconds? Somewhere along the way, the forming star must have shed most of the spin it should have inherited. The answer reveals that nature has clever ways of getting rid of excess rotation. And it brings us back to that flattened disk of material surrounding the young star. The young sun did not keep all the spin of its parent cloud, and the disk is the reason why. As material spiraled inward to feed the growing star, it carried angular momentum with it. But not all of that angular momentum reached the center. Through a slow, intricate process, the inner parts of the disk pass their spin outward to the outer parts, like dancers handing energy down a line. Friction within the disk, along with magnetic forces threading through the gas, allowed material near the center to surrender its rotation and fall inward, while material further out absorbed that rotation and drifted outward. In this way, the disk acted like a great sorting machine, sending mass inward to build the star, while sending angular momentum outward to be carried away. The young sun also helped shed its spin in a more direct way. Newborn stars are violent. They blast out powerful winds of charged particles, streaming away from their surfaces into space. These winds are tied to the star's magnetic field, and as the star rotates, the field acts like a long lever arm, flinging the escaping particles outward and carrying angular momentum away with them. It is a bit like a spinning skater throwing weights off into the distance. Each thrown weight carries away some spin, and the skater slows down. Over millions of years, the young sun threw off enough of its angular momentum through these winds to settle into the calm, 25-day rotation we see today. So the leisurely spin of our sun is not a sign that it inherited little rotation. It is a sign that the sun worked hard to get rid of most of it, handing it off to the disk and flinging it into space. The spin had to go somewhere, because angular momentum cannot simply vanish. And much of it ended up in the orbits of the planets. This is one of the most elegant facts in the study of our solar system. If you add up all the angular momentum in the system, you find something surprising. The sun, despite holding the overwhelming majority of all the mass, carries only a small fraction of the total spin. The great bulk of the angular momentum lives in the orbits of the planets, especially the giant ones, Jupiter and Saturn, which swing around the sun at great distances. The mass is concentrated in the center, but the spin is concentrated in the orbits far outside. This is exactly what we would expect if the forming sun shed its rotation outward into the surrounding disk, where the planets were taking shape. The architecture of our solar system carries, written into it, the record of how spin was passed around during its birth. When you understand this, the layout of our solar system stops being a random collection of worlds and becomes a beautifully consistent story. A spinning cloud, collapsing and flattening, shedding its excess rotation outward, building a calm central star surrounded by a retinue of orbiting planets, all turning in the same direction, all lying in nearly the same plane. Every piece fits, and the same story, with countless variations, has played out around billions upon billions of other stars across the galaxy. This raises a wonderful thought. If spin shapes solar systems so reliably, then the disks we see forming around other young stars should be producing planets that share the same family traits. And indeed, that is what we find. Across the galaxy, astronomers have discovered thousands of planets orbiting other stars, worlds we call exoplanets. Many of them orbit in flattened systems, circling their stars in roughly the same plane, just as the planets do in our own neighborhood. The same physics of the spinning disk appears to operate everywhere, sculpting flattened systems of orbiting worlds around star after star. The universe is not making each solar system from scratch with its own rules. It is following the same recipe, over and over, governed by the simple, relentless logic of rotation and gravity. And yet, exoplanet systems also show us that the recipe allows for astonishing variety. Some systems are packed tight, with several planets crammed into orbits closer to their star than Mercury is to our Sun. Others contain giant planets whirling around their stars in just a few days, so close that their surfaces are scorched to thousands of degrees. Some planets follow tilted or stretched orbits, hinting at violent histories of collisions and gravitational struggles. In each case, the spin and the disk set the stage, but the chaotic drama of formation, with its impacts and near misses and gravitational tugs of war, wrote a unique ending. This is the balance the universe so often strikes. A deep, simple rule underneath, conservation of angular momentum, producing endless diversity above. Now let us return to the worlds themselves and look at how spin shapes not just their formation, but the conditions for everything that lives upon them. The rotation of a planet does far more than create day and night. It stirs the atmosphere and the oceans, driving the weather and the climate. On a rotating planet, moving air and water do not travel in straight lines. They are deflected, curved aside by the planet's spin in a phenomenon you may have heard of, named after the scientist who described it, the Coriolis effect. This deflection is why great storm systems on Earth swirl rather than simply blowing in straight lines. Hurricanes and cyclones spin because the planet beneath them spins, their winds curved into vast rotating spirals. The same effect organizes the prevailing winds that circle the globe and the great currents that wind through the oceans, distributing heat from the equator toward the poles. Without rotation, our planet's weather would behave in an utterly different way, with heat moving in simpler, less dynamic patterns. The spin of the Earth is woven into the very fabric of our climate. It even shapes the protective shield that guards life from the harshness of space. Deep inside the Earth lies a core of molten and solid metal, mostly iron, churning slowly over the ages. As the planet rotates, this liquid metal moves in great circulating currents, and that motion generates electric currents, which in turn produce a magnetic field. This is the source of Earth's magnetism, the invisible field that surrounds our entire planet and reaches far out into space. That magnetic field is no minor detail. It deflects much of the stream of charged particles that constantly flows outward from the sun, the relentless solar wind. Without this shield, that wind could slowly strip away our atmosphere, eroding the very air we breathe over the eons. The spinning of Earth's metal core, in other words, helps protect the conditions that allow life to flourish on the surface. And once again, spin is at the heart of it. The same circulating motion, driven in part by the planet's rotation, raises the magnetic shield that makes Earth so hospitable. Compare this with Mars. Mars is smaller than Earth, and long ago its interior cooled and its churning slowed. Its global magnetic field faded away. Without that protective shield, the solar wind was free to strip away much of the Martian atmosphere over billions of years, leaving the thin, cold air that the planet has today. The story of Mars is, in part, the story of a world whose inner engine wound down, a cautionary tale of what can happen when a planet loses the dynamism that a healthy spin and a hot, moving interior provide. Spin, then, is not merely a curiosity of physics. On a living world, it is bound up with weather, climate, and the very protection of the atmosphere. It shapes the conditions under which life can take hold and endure. Now, consider what happens to a planet's spin over the longest stretches of time, because here too there are surprises. We have already seen how the moon slowly breaks Earth's rotation, lengthening our days. But the moon does something else for us as well, something quietly essential. It steadies the tilt of our planet. Earth spins on an axis that is tilted relative to its orbit around the sun, and this tilt is the reason we have seasons. As the planet travels around the sun, the first one hemisphere and then the other leans toward the warmth, giving us summer and winter in their turn. That tilt is currently a little over 23 degrees, and it has stayed remarkably stable over long periods. The reason it stays stable is, in large part, the moon. The gravitational presence of our large moon acts like a stabilizer, holding the tilt of Earth's axis steady against forces that would otherwise nudge it back and forth over time. Without the moon, calculations suggest that Earth's tilt could wander wildly over millions of years, swinging through large angles. Such swings would cause dramatic, chaotic shifts in climate, with the poles sometimes tipping toward the sun and the seasons lurching into extremes. The relative steadiness of our seasons, which life on Earth has depended upon, owes a quiet debt to the spin and the orbit of our companion in the sky. Let us step back and confront a question that may be quietly nagging at you. Why does angular momentum get conserved at all? Why does the universe insist on this strange bookkeeping, never letting spin simply disappear? The answer reaches into one of the most profound ideas in all of science, an idea about symmetry. In the early 20th century, a brilliant mathematician named Emmy Noether proved a remarkable theorem. She showed that every conservation law in physics is tied to a symmetry in the laws of nature. The conservation of energy, for instance, is tied to the fact that the laws of physics do not change over time, that an experiment done today gives the same result as the same experiment done tomorrow. And the conservation of angular momentum is tied to a beautiful fact about space itself. Space has no preferred direction. The laws of physics work exactly the same whether you face north, south, east, or any direction at all. There is no special axis built into the universe, no cosmic up or sideways that nature favors. Because of this perfect rotational symmetry of space, angular momentum must be conserved. The two facts are inseparable, two faces of the same deep truth. This is a stunning realization. The reason a figure skater speeds up when she pulls in her arms, the reason a collapsing star spins faster, the reason planets all turn in the same direction, traces back to the simple, profound fact that space looks the same in every direction. The conservation of spin is not an arbitrary rule. It is a direct consequence of the symmetry of the universe. When you watch something spin, you are watching that deep symmetry express itself in motion. There is something almost poetic in it. The very evenness of space, its refusal to prefer any one direction, is what guarantees that rotation, once begun, endures. A featureless, directionless emptiness gives rise to the relentless persistence of the spin. Let us now travel back down from these lofty heights and look at the smallest scales, because spin appears there too. in a form stranger than anything we have yet discussed. Deep within the atoms that make up your body, the particles themselves carry a property that physicists call spin. Electrons, protons, and many other fundamental particles each possess this intrinsic spin, a kind of built-in angular momentum that they always have and can never lose. But here the word spin becomes a little misleading. These particles are not tiny balls, physically rotating like a top. As far as we can tell, an electron has no size at all, no surface to whirl around. And yet it behaves, in every measurable way, as though it carries a fixed amount of rotational motion. This quantum spin is one of the most fundamental properties a particle can have, as basic as its mass or its electric charge. It is woven into the deepest layers of reality, and it follows its own strange rules, rules that belong to the bizarre world of quantum mechanics. This quantum spin is not just an abstract curiosity. It shapes the world you live in every single day. The way electrons arrange themselves around atoms, which depends on their spin, determines how atoms bond together to form molecules. In a very real sense, the chemistry of everything around you, the structure of water, of air, of your own flesh, rests upon the spin of particles too small to ever see. Quantum spin is also the foundation of magnetism. When the spins of many electrons in a material line up together, pointing the same way, their combined effect produces a magnetic field. This is why a simple iron magnet can hold a note to your refrigerator door. The magnetism springs from the aligned spins of countless electrons within the metal. The same property even underlies some of the most powerful tools of modern medicine. The machines that take detailed images of the inside of the human body, allowing doctors to peer at organs and tissues without a single cut, work by manipulating the quantum spin of particles within your body and listening to how they respond. A property of nature so fundamental and so small touches your life in ways you might never have imagined. So from the unimaginably vast to the unimaginably tiny, spin runs through everything. The whirl of galaxies and the intrinsic turning of an electron are governed by versions of the same underlying principle: angular momentum, expressed across scales separated by an almost incomprehensible gulf. It is one of the great unifying threads of physics, connecting the cosmos to the atom. Let us return now to the largest of the large, and consider some of the most extreme spinning objects the universe has ever produced. To fully appreciate just how far the figure skater principle can be pushed, we have already met neutron stars, those collapsed cores spinning hundreds of times each second. But to truly grasp what that means, picture the scene in detail. Imagine an object holding more mass than our entire sun, yet squeezed into a sphere no larger than a city. Now imagine that city-sized object turning so fast that it completes hundreds of full rotations in the time it takes you to blink. The surface of such a star, at its equator, races around at a speed that is a substantial fraction of the speed of light itself. The gravity at its surface is so intense that a pebble dropped from even a small height would strike the ground at a speed beyond anything our intuition can handle. And threading through and around this object are magnetic fields of staggering power, the strongest magnetic fields known anywhere in the universe. When such a magnetic field is dragged around hundreds of times per second by the star's spin, it generates the lighthouse beams that we detect as pulsars. These objects are so extreme that they serve as natural laboratories, allowing physicists to test their theories under conditions that could never be created on Earth. By timing the flashes of pulsars with extraordinary precision, scientists have confirmed predictions about gravity, about the structure of matter, and about the warping of space and time. A spinning, collapsed star, ticking away in the dark, becomes a tool for probing the deepest laws of nature. Sometimes, two of these extreme objects find themselves bound together, locked in a gravitational embrace. A pair of neutron stars, or even a pair of black holes, can orbit one another, circling closer and closer over millions of years. As they spiral inward, they whirl around each other faster and faster, their orbital spin accelerating toward a frantic climax. In the final moments before they merge, these objects can be circling one another hundreds of times every second, their combined motion warping the very fabric of space around them, and then they collide. When two such objects merge, they send ripples spreading outward through the fabric of space and time itself, waves of pure distortion called gravitational waves. These waves carry away enormous amounts of energy, much of it drawn from the spinning, orbital dance of the two objects. In the final fraction of a second of one such merger, the power radiated in gravitational waves can briefly exceed the combined light of every star in the observable universe. For the first time in history, in recent years, we built instruments sensitive enough to detect these waves directly. When the signal arrived, it carried the unmistakable signature of two massive objects spiraling together and merging, their orbital spin winding up into a final, ringing crescendo. We had, in effect, heard the sound of spinning space itself. It was a triumph that opened an entirely new way of observing the universe, and at its heart was the spin of orbiting bodies, played out under the most extreme conditions imaginable. The merged object left behind by such a collision is itself spinning, born turning from the union of its two whirling parents, carrying their combined angular momentum into its new existence. Spin begets spin, passed from one generation of objects to the next, conserved through even the most violent events the cosmos can produce. Let us now widen our view once more and think carefully about galaxies, because their rotation tells an even richer story than we first glimpsed. A galaxy like the Milky Way is not a solid object turning as one piece. Like the Sun, it rotates differentially, with different parts moving at different speeds. But the way a galaxy rotates is profoundly strange, and it was studying this strangeness that helped reveal the hidden universe. In our solar system, the planets closest to the Sun orbit fastest, and those farthest away orbit slowest, because the Sun's gravity weakens with distance. This is exactly what we would expect when most of the mass sits at the center. When astronomers looked at galaxies, they expected the same pattern. Stars near the center should orbit quickly, and stars far out in the sparse outskirts should orbit slowly, trailing behind. But that is not what they saw. Instead, stars far out near the edges of galaxies were orbiting just as fast as stars much closer in. The rotation did not fall off with distance the way it should. It stayed stubbornly flat, all the way out to the visible edge and beyond. This was a genuine shock. There seemed to be only two possibilities. Either our understanding of gravity was somehow wrong, or there was a great deal of unseen mass spread throughout these galaxies, providing the extra gravity needed to keep the outer stars whirling so quickly. Most evidence has pointed toward the second answer. There appears to be a vast, invisible halo of matter surrounding each galaxy, extending well beyond the visible stars, holding everything together with its gravity. This is the dark matter we spoke of earlier, and it was the careful measurement of how galaxies spin that first revealed its presence so clearly. A pioneering astronomer named Vera Rubin, studying the rotation of galaxies in the middle of the 20th century, gathered some of the most compelling early evidence for this hidden mass. By measuring how fast stars moved at different distances from the centers of galaxies, she found again and again that the outer regions were moving too quickly to be held by visible matter alone. Her work helped transform dark matter from a fringe idea into one of the central puzzles of modern science. It is a beautiful example of how a simple question about spin, asking merely how fast the stars in a galaxy go around, can crack open a mystery that reshapes our entire picture of the cosmos. To this day, we do not know what dark matter actually is. We have searched for it with sensitive detectors buried deep underground, with powerful particle accelerators, and with telescopes scanning the sky. We have measured its effects in great detail, mapping how its gravity bends light and binds galaxies, yet its fundamental nature remains hidden. What we do know is that the way galaxies rotate cannot be explained without it, or without some equally dramatic revision of our understanding. The spin of galaxies is one of our clearest windows onto the dark, unseen majority of the universe. There is even more that galactic rotation reveals. The direction in which a galaxy spins, and the way that spin relates to its neighbors, carries clues about how galaxies form and grow. Galaxies are not born in isolation. They grow by merging, by drawing in smaller galaxies and clouds of gas, building themselves up over billions of years. Each time a galaxy swallows another, the spin of the newcomer is added to the mix, sometimes reinforcing the host's rotation, sometimes disrupting it. A galaxy's spin, then, is a record of its history, a summary of all the mergers and acquisitions that built it. Some galaxies have smooth, orderly rotation, suggesting calm histories with few major disruptions. Others are chaotic, with stars moving in tangled, disordered ways, the signature of violent collisions in their past. By studying how galaxies spin, astronomers can read something of their life stories, reconstructing the long, slow process by which the great structures of the cosmos assembled themselves. And our own Milky Way is part of this ongoing drama. Our galaxy is itself the product of past mergers, and it is heading toward another one. The Great Spiral of Andromeda, our nearest large galactic neighbor, is drifting toward us across the gulf of space. Billions of years from now, the two galaxies will meet and merge, their stars sweeping past one another, their structures dissolving and reforming. When that happens, the combined spin of both galaxies will determine the shape of whatever emerges from the collision. The orderly spiral arms we know today may give way to a rounder, more chaotic form, with stars orbiting in many different directions. Even on these grandest of scales, spin is the quantity that decides how things will turn out. Quite literally, shaping the future of galaxies. Let us pause and reflect on just how deep this pattern goes. We began with the feeling of stillness as you sit reading or listening, and we found that stillness to be an illusion, a tapestry of motions, all moving together. We traced spin from the gentle drift of a collapsing cloud to the calm turning of our sun, from the orderly orbits of the planets to the wild whirl of neutron stars, from the swirling of black holes to the majestic rotation of entire galaxies. At every level, the same principle held. Rotation, once present, persists, and when matter gathers inward, that rotation intensifies. But there is a question we have not yet fully answered, and it is perhaps the most natural one of all. Where did the very first spin come from? We said that clouds inherit their rotation from the turning of the galaxy. But where did the galaxy get its spin? And what about the earliest structures in the universe? The first clouds of gas to collapse, before any galaxies existed to seed them. To answer this, we have to travel all the way back to the beginning of everything, to the universe in its infancy. In the earliest moments after the universe began, matter was spread out with astonishing smoothness. The young cosmos was nearly uniform, almost the same everywhere. A hot, dense, expanding sea of particles and radiation. But it was not perfectly uniform. There were tiny ripples, minuscule variations in density, places where matter was packed just slightly more tightly than average, and places where it was slightly thinner. These ripples were extraordinarily small, mere whispers of unevenness in an otherwise smooth expanse. Yet they were the seeds of everything. As the universe expanded and cooled, gravity went to work on these ripples. The slightly denser regions pulled in more matter, growing denser still, while the thinner regions emptied out. Over millions of years, this process amplified the tiny ripples into great clumps and filaments of matter, the scaffolding upon which galaxies would later form. And here, at last, we find the origin of cosmic spin. As these clumps of matter grew and pulled on one another, they tugged on their neighbors with gravity. A clump did not simply fall straight toward the nearest concentration of mass. It felt pulls from many directions at once, from clumps to one side and clumps to the other, each tugging at a slightly different angle. These off-center, lopsided pulls did not draw matter in along a single straight line. They imparted a twist. Astronomers call this process tidal torquing, and it is thought to be the source of the rotation of galaxies. In the early universe, every forming structure was gravitationally tugged by its neighbors from many sides, and those uneven tugs set it gently turning. No structure could fall together perfectly symmetrically, because the matter around it was never arranged with perfect symmetry. There was always some lopsidedness, some imbalance in the surrounding pulls. And just as with the collapsing cloud, that initial gentle twist was then amplified as the structure contracted, conserving its angular momentum and spinning faster as it drew inward. So, the spin of galaxies, and ultimately the spin of everything within them, traces back to the gravitational tugs of the early universe, acting on its tiny initial ripples. The faint unevenness of the newborn cosmos, magnified by gravity over billions of years, set the entire universe turning, structure by structure, in countless different directions. This is why almost everything spins, and yet the universe as a whole does not. Each structure received its own twist from its own particular neighborhood of gravitational pulls. Those twists point in random directions, scattered across the sky, because the arrangement of matter around each forming galaxy was effectively random. Add them all together, and they cancel. The universe is full of spin, born from the chaos of gravity acting on tiny ripples. Yet that spin has no overall preferred direction, because the ripples themselves favored no direction at all. It is a profound and satisfying resolution. The same randomness that guarantees almost every individual structure will spin also guarantees that the grand total of all that spinning is very nearly nothing. The cosmos is a churning sea of countless whirlpools, each turning its own way, the whole somehow remaining serene and balanced. When we trace the lineage of any spinning thing, the chain stretches back through an unbroken sequence of inheritance and amplification. The Earth spins because the cloud that formed it spun. The cloud spun because the galaxy that held it spun. The galaxy spun because of the gravitational tugs of the early universe. And those tugs arose from the faint, primordial ripples present in the cosmos, almost from the very beginning. When you feel the day turn from light to dark, you are feeling the final, faint echo of a process that began in the first moments of the universe, passed down across nearly 14 billion years through cloud and star and world, until it became the simple turning of the ground beneath your feet. There is still more wonder to be found in the consequences of spin, and some of the most beautiful sights in the solar system owe their existence to it. Consider the rings of Saturn, perhaps the most breathtaking spectacle our cosmic neighborhood has to offer. Those rings are not solid bands. They are made of countless particles of ice and rock, ranging from grains smaller than a snowflake to chunks the size of a house, each one orbiting Saturn independently. And all of them orbit in the same direction, lying in a thin, flat sheet around the planet's equator. Why a flat sheet rather than a sphere or a thick cloud? For the same reason the planets lie in a flat plane around the Sun. A swirling collection of orbiting particles naturally settles into a thin disk, flattened by collisions and shaped by the planet's spin and gravity. The rings of Saturn are a miniature echo of the great protoplanetary disk that once surrounded the young Sun, a living demonstration of the same physics that built our solar system, preserved and glowing around a single planet. When you look at an image of those rings, you are seeing the principle of the flattened spinning disk made visible, suspended in space for us to admire. The same flattening shapes other structures too. The asteroid belt, that band of rocky debris between Mars and Jupiter, lies roughly in the same plane as the planets, another remnant of the original disk. And far out beyond the planets, a vast belt of icy bodies circles the Sun in the same flattened arrangement. The frozen leftovers of the solar system's formation, still tracing the shape of the disk that bore them. Even the comets, those wanderers that occasionally blaze across our skies, tell a story of spin. Many of them originate from the flattened outer belt and travel on orbits that reflect the rotation of the system they belong to. When a comet swings close to the Sun and grows a magnificent tail, it is a visitor from the frozen edges of a spinning system, briefly lit up for us to witness. The whole solar system, from the Sun at its center to its most distant icy outskirts, is organized by rotation into nested rings and disks and orbits, all turning in concert, all bearing the imprint of that first spinning cloud. Now, let us turn to a subtler aspect of spin, one that reveals just how rich the physics of rotation can be. A spinning object does not only rotate, it can also wobble. If you have ever watched a spinning top as it begins to slow, you may have noticed that its axis does not stay perfectly upright. Instead, the axis itself slowly traces out a circle, leaning over and swinging around in a stately wobble. This wobble is called precession, and it happens whenever a force tries to tip a spinning object. Rather than simply falling over, a spinning object responds to such a push by precessing, its axis circling slowly around. The Earth does this too. Our planet is not a perfect sphere. It bulges at the equator because of its spin, and the gravity of the Sun and the Moon tugs on that bulge, trying to straighten the tilt of Earth's axis. But because the Earth is spinning, it does not simply tip over. Instead, its axis precesses, slowly swinging around in a great circle that takes about 26,000 years to complete. This means that the direction Earth's axis points in the sky gradually shifts over the centuries. Today, the northern axis points close to the star we call Polaris, the North Star, which is why that star sits almost directly above the North Pole and barely moves in the sky. But thousands of years from now, the axis will point elsewhere, and a different star will take up the role of the pole star. In the distant past, the people who built the great monuments of antiquity saw a different star marking the north, because the slow precession of Earth's axis had it pointing in another direction. This grand, slow wobble also gradually shifts the timing of the seasons relative to Earth's position in its orbit, contributing over tens of thousands of years to the long, rhythmic changes in our planet's climate. The slow precession of the spinning Earth is woven into the rise and fall of ice ages, into the deep, patient cycles that have shaped the history of life and landscape on our world. A spinning top wobbling on a table and the slow turning of the heavens above us are, at heart, the same phenomenon, the same physics of rotation expressed across vastly different scales of size and time. This stability of a spinning axis, the way it resists being tipped and instead holds its direction, is itself enormously useful. A spinning object tends to keep its axis pointed in the same direction, stubbornly maintaining its orientation against forces that try to disturb it. This property is the basis of the gyroscope, a spinning wheel that holds its orientation steadily in space. Gyroscopes guide ships and aircraft and spacecraft, helping them know which way they are pointed and keeping them steady on their courses. The same physics that makes a spinning top resist falling over allows a spacecraft to navigate the void, using the steadfastness of a spinning wheel as a compass that needs no magnetic field. Spin, in this guise, becomes a tool, a source of stability that humans have harnessed to find their way. There is something deeply fitting in that. The very persistence of rotation, the way a spin holds its direction and refuses to simply fade, which began as a property of collapsing clouds and forming worlds, becomes in our hands an instrument of guidance and exploration. We are made of spinning matter, born on a spinning world, in a spinning galaxy, and we have learned to use the steadfast nature of spin to steer our way through the cosmos. Let us return to the deeper question of why spinning matter flattens into disks, because it lies at the very heart of so much that we have discussed, and it deserves to be understood clearly. Imagine a cloud of particles, all orbiting a common center, but in many different directions and at many different tilts. Some orbit clockwise, some counterclockwise, some tilted steeply, some lying flat. Now let these particles collide with one another, as they inevitably will in a dense, swirling cloud. When two particles moving in opposite directions collide, their motions tend to cancel, and they lose energy. But there is one quantity they cannot lose in these collisions, taken all together, and that is the total angular momentum of the whole cloud. The collisions bleed away the disorganized, up and down, back and forth motions, converting that energy into heat which radiates away. But the net spin, the overall sense of rotation that all those motions add up to, cannot be destroyed. So the cloud settles. The chaotic, every which way motions are damped out by collisions, while the overall rotation remains. What survives is a flattened disk, with all the particles orbiting in the same direction, in the same plane, the plane defined by the net angular momentum of the original cloud. This is why disks form everywhere in the universe. Around young stars, around black holes, around planets in the form of rings. The same process plays out. Collisions flatten the chaos, and the surviving spin defines a plane. A disk is what you get when you let a spinning cloud relax as much as it can while still holding on to its angular momentum. It is the natural, almost inevitable shape of orbiting matter that is allowed to collide and settle. And once you see this, you begin to recognize disks everywhere you look in the cosmos. The flat plane of our solar system, the rings of the giant planets, the swirling disks of gas-feeding black holes, the broad, flattened shapes of spiral galaxies. All of them are expressions of the same underlying truth. Spinning matter, allowed to settle, becomes a disk. The universe is decorated with these flattened, spinning structures. From the scale of a planet's rings to the scale of an entire galaxy, each one a monument to the persistence of angular momentum. It is worth pausing to marvel at how a single principle, conservation of angular momentum, ties together such a sweeping range of phenomena. The figure skater on the ice, the flattening of a young solar system, the dizzying spin of a neutron star, the formation of a black hole's accretion disk, the gentle wobble of a spinning top, the steadfast pointing of a gyroscope, the flat plane of the planets, the rings of Saturn, the rotation of galaxies, and the hidden dark matter it reveals. All of these, every one, flow from the same deep idea. Few principles in all of science reach so far, connecting the everyday to the cosmic, the tiny to the immense. It is illuminating to imagine, for a moment, what the universe would be like if spin did not exist, if somehow matter could collapse without ever rotating. In such a universe, a collapsing cloud would simply fall straight inward, every particle plunging directly toward the center along a straight line. There would be no disk, no flattening, no orbiting material left over to form planets. The cloud would crash together into a single point of matter, with nothing circling it. There would be no solar systems as we know them, no families of planets tracing graceful orbits, no flat plains of worlds. A star might form, but it would stand alone, without the retinue of planets that rotation makes possible. Without spin, there would be no stable orbits, and without stable orbits, there would be no place for a planet like Earth to circle a star at a comfortable distance for billions of years. The very existence of planets, and therefore of any life that lives upon them, depends on the fact that matter rotates. Spin is what holds a planet in its orbit, perpetually falling toward its star yet perpetually missing, tracing a stable path year after year. Take away the spin, and the planet would simply fall into the star or never form at all. In this sense, we owe our very existence to rotation. The Earth does not plunge into the sun because it is moving sideways as it falls, circling endlessly in an orbit that is itself a kind of spin. This delicate balance between the pull of gravity drawing us inward and the sideways motion carrying us around is what gives us a stable home in the warmth of the sun's light. That balance is angular momentum at work, the same principle we have followed across the whole vast story. A universe without spin would be a sterile place of lonely stars and infalling matter, with no stable worlds and no living things to wonder about any of it. It is rotation that fills the cosmos with structure, with orbiting worlds and turning galaxies and the long, stable expanses of time that life requires. When we ask why everything spins, we are, in a way, asking why the universe is the kind of place that can contain us at all. The answer is that spin is woven into the fabric of how matter behaves, and that same spin is what makes possible the stable, structured, enduring cosmos in which life can arise. There is a quiet beauty in recognizing that the turning of the world is not incidental to our existence, but essential to it. We are not merely passengers on a spinning planet. We are children of spin, made possible by the rotation that shaped our world and held it in its life-giving orbit. Now, let us consider the future and ask what becomes of all this spinning over the vast stretches of time still to come. Spin is remarkably persistent, but it is not entirely eternal, and over immense spans of time, it slowly redistributes itself. We have seen how Earth's rotation gradually slows as it hands angular momentum to the Moon. Far in the future, this process will continue. The days will grow longer and longer, stretching out over hundreds of millions and then billions of years. Eventually, in the very distant future, Earth and Moon may settle into a state where the Earth always shows the same face to the Moon, just as the Moon already shows the same face to us, the two locked together in a slow, mutual embrace. Whether our planet survives long enough for that to happen is another question, for the Sun itself has a finite life, and its eventual transformation into a swollen, dying star will reshape the inner solar system long before that final locking could occur. But the principle stands. Wherever there is tidal interaction, spin slowly flows from one body to another, smoothing and synchronizing rotations over the eons. On the largest scales, the spinning of galaxies will continue for an unimaginably long time, for there is little to slow their majestic rotation. Galaxies will go on turning, long after their stars have aged, long after new star formation has ceased, wheeling slowly in the dark for timescales that dwarf the current age of the universe. Even when the lights of a galaxy have dimmed, its rotation will persist, a ghostly memory of the spin it inherited at birth, conserved through the long, cold future. Black holes, too, will hold their spin across almost inconceivable spans of time. A spinning black hole can retain its rotation for periods so vast that the numbers lose all meaning, turning quietly in the emptiness as the universe ages around it. In the deep future, when stars have burned out and matter has grown sparse and cold, spinning black holes may be among the last structures still bearing the imprint of the rotation that pervaded the younger cosmos. In this way, spin is among the most enduring legacies of the universe, outlasting the light of stars, persisting in the turning of galaxies and the rotation of black holes long after almost everything else has faded. The cosmos began with the faintest of twists, imparted to forming structures by the gravity of their neighbors, and that twist will echo onward into the deepest reaches of time. From the first ripples to the last black holes, spin threads through the entire history of the universe, a quiet, constant companion to the unfolding of cosmic time, and throughout all of it, the same principle reigns. Angular momentum is conserved. Spin can be passed from one body to another, sped up by collapse, slowed by tides, transferred through gravity, but never simply destroyed. It flows through the universe like a current, ever changing hands, ever conserved, an unbroken thread running from the beginning to the far future. It is worth reflecting on how we even came to know all of this, because the story of how humans discovered the universal nature of spin is itself a remarkable journey. For most of human history, people did not realize the Earth was spinning at all. The ground felt solid and still, and the sky appeared to wheel overhead. It seemed obvious that the heavens turned around a motionless Earth. The idea that our planet itself was the thing turning, racing around its axis at over 1,000 kilometers per hour, was a radical and unsettling proposal. It took centuries of careful thought and observation to overturn the intuition of stillness. When thinkers first suggested that the apparent turning of the sky was really caused by the rotation of the Earth, many objected. If the Earth were spinning so fast, they asked, why were we not flung off? Why did the winds not roar constantly against the direction of the spin? Why did objects thrown into the air not land far behind us? The answers required a deeper understanding of motion, an understanding that everything on the Earth moves along with it, sharing its spin so that we feel no wind and notice no flinging. A clever demonstration eventually settled the matter beyond doubt. A long pendulum, set swinging freely, was observed to slowly change the direction of its swing over the course of a day. The pendulum was not really changing direction. The Earth was turning beneath it. Here, at last, was direct, visible proof that the ground beneath our feet is in constant rotation, a quiet, elegant experiment revealing the spin we cannot feel. From that foundation, our understanding grew. As telescopes improved, astronomers watched the sun and saw its spots drift across its face, revealing that the sun too was rotating. They watched the planets and tracked their turning, measuring the length of a day on distant worlds. They studied the orbits of moons and the shapes of planets, finding the fingerprints of rotation everywhere they looked. And as our instruments reached further into space, we discovered spin on scales our ancestors could never have imagined. The rotation of galaxies, the whirl of neutron stars, the swirling of matter around black holes. Each discovery extended the same truth outward, revealing that rotation is not a peculiarity of the Earth, but a universal feature of the cosmos. The journey from believing the Earth stood still to understanding that nearly everything in the universe spins represents one of the great expansions of human knowledge. It is a story of overturning what seemed obvious, of replacing the comfortable illusion of stillness with the dynamic, turning reality that science revealed. And it reminds us that our immediate intuitions are not always a reliable guide to the true nature of things. The world feels still, yet it spins. The sky seems to turn, yet it is we who are turning. Learning to see past these illusions, to grasp the real motions hidden beneath our perceptions, is one of the triumphs of the human mind. Let us look more closely at how astronomers actually measure the spin of objects so far away that we can never visit them, for the techniques are ingenious. When an object rotates, one side of it is turning toward us, while the other side is turning away. The side coming toward us has its light shifted slightly toward the blue end of the spectrum, while the side moving away has its light shifted toward the red. By measuring this subtle difference across the face of a star or galaxy, astronomers can determine how fast it is spinning, even across distances of thousands or millions of light years. The light itself carries the signature of the rotation, encoded in tiny shifts of color that careful instruments can read. This is how we know the rotation speeds of distant stars, the turning of galaxies, and the orbital motions of stars within them. For pulsars, the measurement is even more direct. We simply count the flashes. Each flash marks one rotation, and by timing them with great precision, we can determine the spin of a neutron star to extraordinary accuracy, knowing that it turns, say, several hundred times each second. For black holes, measuring spin is subtler still, but possible. The rotation of a black hole affects the behavior of the hot, glowing matter swirling around it, and by carefully studying the light from that swirling disk, astronomers can deduce how fast the black hole at the center is turning. A rapidly spinning black hole leaves a different imprint on the surrounding light than a slowly spinning one, and from these clues we can estimate the spin of objects from which no light can ever escape. Through all these methods, we have built up a picture of spin across the universe, confirming again and again that rotation is everywhere, on every scale we can probe. We have measured the lazy turning of slow stars and the frantic whirl of the fastest pulsars. We have charted the rotation of galaxies near and far, finding the same puzzling flatness that points to dark matter throughout the cosmos. We have estimated the spins of black holes from the light of the matter falling into them. Everywhere we look, with every technique we devise, we find the same answer: things turn. The universe is in motion, rotating at every level, exactly as the deep principles of physics predict. And this universal spinning is not random noise, but an orderly consequence of how matter behaves under gravity, of how clouds collapse and conserve their angular momentum, of how the gentle tugs of the early universe set everything turning long ago. The more we measure, the more the picture holds together, a vast, coherent story of rotation reaching from the atom to the galaxy and beyond. Each new observation is another confirmation that we have grasped something true about the nature of the cosmos, something that ties the whole of it together into a single, comprehensible pattern. Return for a moment to our own sun, because its spin holds a rhythm that touches our lives more than we often realize. The sun's differential rotation, with its equator turning faster than its poles, winds up its magnetic field over time into an ever more tangled, twisted state. This winding builds and builds until the magnetic field becomes so knotted that it reorganizes itself, settling into a new arrangement before beginning to wind up all over again. This great cycle of winding and reorganizing takes roughly 11 years, and it governs the rhythm of the sun's activity. At the peak of the cycle, when the magnetic field is most tangled, The sun is dotted with many spots and erupts frequently with flares and outbursts. At the quiet end of the cycle, the sun grows calmer, its face cleaner, its eruptions less frequent. This 11-year solar cycle, driven by the sun's rotation, has real effects on Earth. During active periods, the increased eruptions can disturb our magnetic field, light up our skies with brilliant auroras, and occasionally interfere with our satellites, our communications, and even our power grids. The turning of the sun, twisting its magnetic field through this long cycle, reaches across millions of kilometers of space to touch our technology and our skies. Even the gentle, steady rotation of our calm and ordinary star has its consequences for life on Earth, woven into the rhythms of space weather that wash over our planet. It is humbling to realize that the same principle which lit the sun and shaped the planets also drives this slow magnetic heartbeat, pulsing every 11 years, a rhythm set in motion by rotation. And the sun is, by cosmic standards, an unremarkable star, a calm and middle-aged member of a vast galactic population. Around other stars, spin drives phenomena far more violent, with magnetic eruptions and stellar storms that dwarf anything our sun produces. Young stars in particular spin rapidly and rage with activity, their fast rotation generating powerful magnetic fields and frequent, ferocious outbursts. Over time, as a star ages and sheds its angular momentum through its stellar wind, it spins down and grows calmer, much as our own sun has done over its long life. In a sense, the spin of a star is a measure of its youth. Fast-spinning stars tend to be young and active, while slow-spinning stars tend to be older and more settled. Astronomers can even estimate the age of a star by measuring how fast it rotates, reading its history and the speed of its turning. The gradual slowing of a star's spin over billions of years becomes a kind of clock, marking the passage of stellar time. Our sun, spinning at its leisurely 25-day pace, is a star in its calm middle age, having long since shed the wild rotation of its youth, settling into the steady rhythm that has allowed life the stability it needed to flourish on Earth. Let us also dwell on the strange exceptions, the worlds and objects whose spin defies the usual pattern, because they are not just curiosities. They teach us that the universe, for all its underlying order, is shaped by chance and chaos as well. We saw that Venus turns backward and turns with extreme slowness, and that Uranus lies tipped over on its side. These are reminders that the orderly inheritance of spin from the birth cloud is only the starting point of a world's story. After a planet forms, it enters a long and often violent history. Giant impacts can flip a world over, reverse its rotation, or knock its axis askew. The gravitational tugs of other planets and of the sun can slow a spin, alter a tilt, or reshape an orbit over millions of years. By the time we observe a planet today, its spin reflects not only its origin but everything that has happened to it since. The rotation of a world is a palimpsest, a record written and overwritten by collisions and gravitational encounters across the ages. This is why the worlds of our solar system, though all born from the same disk, display such a variety of rotations. Some spin quickly, some slowly, some upright, some tipped, some forward, some backward. Each is the product of a unique history, a different sequence of impacts and tugs and tidal interactions. In their differences, they record the chaotic drama of the solar system's youth, a time of frequent collisions and gravitational upheaval, when the orderly disk was still settling into the arrangement we see today. The strange spinners are not failures of the rule, but illustrations of the richness layered on top of it. The underlying principle, conservation of angular momentum and the inheritance of spin, sets the stage, but the particular story of each world is written by the accidents of its history. This interplay between deep order and contingent chaos runs throughout the cosmos. The laws of physics provide the framework, ensuring that spin arises, that it is conserved, that collapse amplifies it, and tides redistribute it. But within that framework, chance plays out endlessly, producing the vast diversity of objects we observe, each with its own particular spin, its own particular history. The universe is neither rigidly deterministic nor purely random. It is a marriage of law and chance, of pattern and accident, and the spins of its countless objects are among the clearest expressions of that marriage. When we look out at the turning worlds and stars and galaxies, we are seeing both the iron consistency of physical law and the boundless creativity of chance, intertwined in every rotating thing. It is this combination that makes the cosmos endlessly fascinating, forever governed by simple principles, yet forever surprising in its details. Now bring the scale back down, all the way to you. You are made of atoms, and within those atoms, electrons carry their quantum spin, protons and neutrons carry theirs. At the very smallest level of your being, spin is present, intrinsic and unceasing. Build up from there, and you are a body standing on a planet that turns once a day. That planet circles a star, and the motion of that orbit is itself a kind of rotation, a perpetual falling around the sun. The star carries you around the galaxy, a journey so vast it takes hundreds of millions of years to complete a single circuit. And the galaxy turns within a universe full of other turning galaxies, each set spinning by the gravity of the early cosmos. You are, at every level, embedded in rotation. The spin of the particles within you, the turning of your world, the orbit of your planet, the rotation of your galaxy, all of it surrounds and includes you. When you stand still, you are not still at all. You are spinning with the Earth, orbiting with the planet, sweeping around the galaxy, carried along by motions so smooth and so constant that you never feel them. There is a strange comfort in this. The stillness you feel is real in its own way, a stillness relative to the ground and the air and everything around you, all moving together in quiet harmony. But beneath that local calm lies a symphony of motion, a nested set of rotations reaching from the atom to the galaxy, each one turning within the next. You are a small, thinking part of a turning universe, made of spinning matter, standing on a spinning world, gazing out at a sky full of spinning things. And the very fact that you can contemplate all of this, that a portion of the spinning cosmos has organized itself into a form capable of understanding its own rotation, is among the most wonderful facts of all. The universe spins, and within it, you spin too, and somehow you have come to know it. Consider how the largest structures of the universe arrange themselves. For even there, the legacy of rotation and gravity is written across the sky. Galaxies are not scattered randomly through space. They gather along vast filaments, immense threads of galaxies and dark matter stretching across hundreds of millions of light-years, woven into a great cosmic web. Where these filaments cross, galaxies cluster most densely, and between them lie enormous voids, vast emptinesses where few galaxies are found. As matter flows along these filaments, drawn by gravity toward the dense crossing points, it carries angular momentum with it, and the galaxies that form often align their spins with the great structures around them. The orientation of a galaxy's rotation can reflect the direction of the filament it grew within, a subtle echo of the cosmic web imprinted on the turning of individual galaxies. Even on these grandest of scales, the threads of rotation and gravity run together, shaping how galaxies spin and how they are arranged across the universe. The cosmic web itself, this grand architecture of filaments and voids, grew from the same tiny ripples that seeded the spin of galaxies, gravity sculpting the faint initial unevenness into both the great structures and the rotations within them. There is one more remarkable consequence of spin worth exploring, and it concerns the search for life beyond Earth. When astronomers study distant planets around other stars, the rotation of those worlds matters enormously for whether they might be hospitable. A planet that spins at a reasonable pace, like Earth, distributes the heat of its star evenly across its surface, warming the night side and moderating the day side, creating a balanced climate. But a planet that is tidally locked to its star, always showing the same face, faces a very different fate. On such a world, one side bakes in perpetual daylight, while the other freezes in eternal darkness. The contrast between the scorched day side and the frozen night side could be extreme, with powerful winds racing between them, trying to carry heat from the hot hemisphere to the cold. Whether life could survive on such a world is an open question, one that depends in part on how its atmosphere and oceans, if it has them, manage to move heat around the planet. Many of the planets we have found orbiting close to small, cool stars are likely tidally locked in just this way, their rotations slowed and synchronized by the gravity of the star they hug so closely. Understanding the spin of these worlds is therefore central to judging their potential to host life. A planet's rotation shapes its winds, its temperatures, its weather, and ultimately its habitability. In the search for other living worlds, spin is one of the crucial factors astronomers must weigh. The same principle that gave Earth its gentle days and nights, its moderate climate, and its stable seasons may be one of the keys that determines whether a distant world is a haven or a wasteland. And so the humble question of how fast a planet turns becomes bound up with the profound question of whether we are alone in the universe. Spin, which we first encountered as the simple turning of the ground beneath our feet, reaches all the way out to the frontier of one of humanity's greatest quests. It shapes not only the worlds we see, but the very possibility of life upon them, here and perhaps elsewhere among the countless stars. When we imagine other worlds where life might dwell, we must imagine their rotation, the rhythm of their days and nights, the patterns of their weather, all flowing from the spin they inherited and the history that shaped it. In every corner of the cosmos where life might take hold, spin will be there, governing the conditions, setting the rhythms, shaping the possibilities. It is a thread that connects the deepest physics to the most human of questions, whether there is anyone else out there, on some other turning world, gazing up at their own spinning sky and wondering the same things we wonder. The more we learn, the more we see that rotation is not a detail but a foundation, underlying the structure of worlds and the prospects for life across the whole vast, turning universe. Let us linger a little longer on the deep idea at the center of this whole story, because it rewards careful thought. Conservation of angular momentum is not merely a useful rule that happens to describe spinning things. It is one of the great pillars upon which the entire structure of physics rests. Alongside the conservation of energy and the conservation of momentum, it forms part of the bedrock of how we understand motion in the universe. These conservation laws are among the most reliable truths we know. In every experiment ever performed, in every corner of the cosmos we have observed, they hold. Energy is never created or destroyed, only transformed. Momentum is never lost, only transferred. And angular momentum, the measure of spin, is likewise conserved through every interaction, every collapse, every collision. This reliability is what allows us to reason about the universe at all. Because we know spin is conserved, we can look at the calm rotation of the sun and deduce that it must have shed most of its inherited spin somewhere and go looking for where it went. We can look at the dizzying whirl of a neutron star and understand it as the inevitable consequence of a collapsing core conserving its rotation. We can look at the flat plane of the planets and recognize it as the signature of a spinning disk that conserved its angular momentum as it settled. The conservation law is a thread we can follow through the most complex events, a constant amid all the change, allowing us to trace cause and effect across billions of years. And as we saw, this conservation springs from something even deeper, from the symmetry of space itself, its lack of any preferred direction. In a universe where no direction is special, spin must be conserved. The two are inseparable, the evenness of space and the persistence of rotation, bound together by one of the most beautiful theorems in all of physics. When you watch a figure skater pull in her arms and spin faster, you are watching the symmetry of the universe express itself in the most graceful possible way. When a star collapses and spins up into a pulsar turning hundreds of times a second, you are watching the same symmetry played out under unimaginable extremes. The dancer on the ice and the dead star in the dark are governed by the same profound truth, written into the very fabric of space. There is a unity here that the ancient stargazers could scarcely have dreamed of. The turning of the smallest particle and the rotation of the largest galaxy are not separate phenomena, but expressions of a single principle reaching across every scale of the cosmos. To understand spin is to glimpse that unity, to see how the universe, for all its staggering variety, is woven together by a handful of deep and elegant ideas. The question we began with, why does everything spin, opens a door onto the underlying order of reality itself. And behind that door lies a vision of a cosmos held together not by chance, but by symmetry, by conservation, by laws that reach from the atom to the edge of the observable universe. Before we draw this journey to a close, let us gather together the full sweep of what we have seen, the entire chain of spin reaching from the largest to the smallest, from the first moment to the far future. It begins in the infant universe, smooth almost to perfection, marked only by the faintest ripples of unevenness. Gravity seizes those ripples and amplifies them, drawing matter together into clumps and filaments. As these clumps form, the uneven gravitational tugs of their neighbors impart a gentle twist, and the structures begin to turn. This is the birth of cosmic spin, the first rotation, planted by gravity acting on the primordial unevenness of the cosmos. From these turning structures, galaxies condense, inheriting and amplifying the spin as they contract, settling into great rotating disks studded with hundreds of billions of stars. Within a galaxy, clouds of gas drift and swirl, carrying a whisper of the galaxy's own rotation. When such a cloud collapses to form a star, that whisper is amplified into a genuine spin, and the flattened disk around the newborn star gives rise to planets, all orbiting in the same direction, all lying in nearly the same plane. The star itself spins, and so do its planets, and so do the moons that form around those planets, each level inheriting and conserving the rotation passed down from above. On those planets, spin shapes the weather, drives the magnetic fields, steadies or destabilizes the climate, and helps determine whether life might take hold. When a massive star reaches the end of its life and collapses, its spin is concentrated to extraordinary extremes, producing neutron stars that whirl hundreds of times a second, or black holes that drag space itself around with them. And at the very smallest scale, within the atoms that make up every star and world and living thing, particles carry their own intrinsic spin, the quantum foundation beneath it all. From the spin of an electron to the rotation of a galaxy, the same principle reigns, conserved through every transformation, amplified by every collapse, redistributed by every tide and collision. This is the great chain of spin, unbroken from the beginning of the universe to the present day, threading through every scale of existence. When you trace it backward from the turning of your own world, you arrive at the first ripples of the cosmos. When you follow it forward, you reach the distant future of slowly turning galaxies and quietly spinning black holes, persisting long after the stars have faded. Spin is woven into the entire story of the universe, from its smoothest beginning to its coldest, most distant end. It is one of the deepest and most far-reaching patterns in all of nature, and it surrounds you in every moment, in the turning of the ground, the orbit of your planet, the rotation of your galaxy, and the spin of the particles in your very bones. It is worth asking what all of this means for how we see our place in the cosmos. For most of human history, people imagined a still Earth at the center of everything, with the heavens turning around them. We now know that picture was upside down. It is not the heavens that turn around a motionless us. It is we who turn and orbit and sweep through the galaxy, part of a universe in ceaseless motion at every scale. This shift in understanding is more than a correction of fact. It is a transformation in how we relate to the cosmos. We are not the fixed center around which all else revolves. We are participants in a grand, turning dance, carried along by motions far larger than ourselves, sharing in the rotation that pervades all of existence. And yet there is no diminishment in this, only wonder. To know that you are spinning with your planet, orbiting your star, sweeping around your galaxy, is to feel connected to the vast machinery of the universe, to recognize yourself as a part of something immense and beautiful. The same spin that lit the sun and shaped the planets turns the ground beneath you. The same conservation law that governs the whirl of a neutron star governs the orbit that keeps you safely circling your star at a life-giving distance. You are not separate from the spinning cosmos. You are made of it, shaped by it, carried along by it. There is a kind of intimacy in that, a sense of belonging to the universe rather than merely observing it from outside. When you watch the sun set in the evening, you are watching your own world turn, rotating you away from the light, just as it has done every day for billions of years. When you see the stars wheel slowly across the night sky, you are watching the rotation of your planet carry your gaze across the heavens. The turning of the world is not a distant abstraction. It is the most immediate and constant motion of your life, the rhythm that gives you your days and your nights, your mornings and your evenings, the steady pulse of light and dark that has accompanied every living thing on Earth since the beginning. And that turning connects you, through an unbroken chain, to the deepest workings of the universe, to the first ripples of the early cosmos, to the gravity that set the galaxies spinning, to the symmetry of space itself. In the simple fact that the world turns, all of this is contained. The next time you notice the sky growing dark, or watch the long shadows of evening stretch across the ground, remember what that turning truly is. It is the rotation of your world, inherited from the cloud that bore it, passed down from the spinning galaxy, set in motion in the universe's earliest days. It is the same phenomenon that flattens solar systems, lights the sun's magnetic cycle, spins the neutron stars, and wheels the galaxies through the dark. In the turning of your own day, you hold a thread that reaches across the entire cosmos, from the beginning of time to the present moment, from the smallest particle to the largest structure in existence. That is the answer to why everything spins, and that is the wonder hidden within so simple a question. Think, too, about how rare and precious the particular spin of our own world has turned out to be. Earth rotates at a pace that gives us a day length comfortable for life, long enough for the surface to warm under the sun, short enough that the night side never freezes too deeply. Our axis is tilted at an angle that gives us gentle, regular seasons, and that tilt is held steady by the moon, sparing us the wild climatic swings that an unstabilized world might suffer. Our spinning metal core generates a magnetic shield that guards our atmosphere from the erosion of the solar wind. Each of these gifts flows from rotation, and each had to fall within a favorable range for life as we know it to flourish. A world that spun too fast might be racked by ferocious, unrelenting storms. A world that spun too slowly might bake on one side and freeze on the other, or lose the protective dynamo of a moving core. A world tipped too far, or wobbling without a stabilizing moon, might lurch through climatic extremes that life could scarcely endure. Our planet threaded all these needles, ending up with a spin, a tilt, and a companion moon that together created the stable, temperate, sheltered conditions in which life had the time and steadiness it needed to arise and evolve. When we marvel at how well-suited Earth is for life, we are, in part, marveling at the good fortune of its rotation. Among the countless worlds in the galaxy, each with its own spin shaped by its own history, ours happened to land in a fortunate place. This does not mean such worlds are unimaginably rare, for the galaxy holds an enormous number of planets, and surely many others have favorable rotations too. But it does mean that the particular spin of our world is part of what made our existence possible, one of the many quiet conditions that had to be met for a planet to become a home. The turning of the Earth, so easy to overlook, is among the unsung foundations of everything we are, and so we come full circle, back to where we began, to you sitting in apparent stillness while the universe turns around and within you. We asked a simple question: why does everything spin? We have followed that question across the entire cosmos, from the collapsing clouds that birth solar systems to the whirling remnants of dead stars, from the rotation of galaxies to the spin of particles within the atom, from the first ripples of the early universe to the slow turning of black holes in the far future. And we have found a single, elegant answer running through it all. Spin arises because perfect stillness is essentially impossible in a real and turbulent universe, and because whatever faint rotation exists is amplified whenever matter gathers inward under gravity. It is conserved because space itself has no preferred direction, a symmetry so deep that it guarantees rotation will persist. It is inherited and passed down through an unbroken chain, from the early cosmos to the galaxies, to the stars, to the worlds, and to you. This is why everything spins, not by accident, but by the deep logic of a universe built on symmetry and conservation, on gravity and collapse, on the amplification of the faintest initial twist into the turning of worlds and stars and galaxies without end. There is a final thought worth holding on to about the sheer reach of this one idea. When you grasp why everything spins, you have not learned an isolated fact. You have learned a way of seeing that connects things which once seemed entirely separate. The whirlpool draining from a basin, the swirl of a great storm, the wheeling of the stars at night, the flatness of the planets across the sky, the brilliance of a distant quasar, the steady tick of a pulsar, the gentle stability of a spinning top. All of these, once mysteries in their own right, become chapters of a single story once you understand rotation and its conservation. This is one of the quiet joys of understanding the universe. A single principle, grasped clearly, suddenly illuminates 1,000 different things at once. The world becomes less a collection of unrelated wonders and more a single, coherent tapestry, woven through with the same deep threads. Spin is one of those threads. and following it has carried us across the whole of existence, from the atom to the galaxy, from the first instant to the distant future. The ancient observers who watched the stars wheel overhead could not have known that the turning they saw was their own world's rotation, nor that the same turning ran through the sun and the planets, the stars and the galaxies, down into the very particles of which they were made. We are fortunate to live in an age when these connections have been revealed, when we can trace the lineage of spin from the cosmic dawn to the present and understand the deep symmetry that holds it all together. It is a privilege to know these things, to be among the first generations of humans able to answer a question that people must have wondered about for as long as they have watched the sky turn. And the wonder only deepens with understanding. Knowing why everything spins does not drain the mystery from the turning world. It enriches it, layering the simple beauty of a sunset or a starry night with the profound knowledge of what that turning truly is and where it came from. The cosmos loses none of its majesty when we understand it. If anything, it grows more magnificent, more intricate, more astonishing, as we glimpse the elegant principles beneath its endless variety. We began this journey with the strange realization that, even sitting perfectly still, you are spinning, carried along by a planet turning beneath you, an orbit sweeping you around the sun, a galaxy wheeling through the dark. We have traveled from the gentle drift of a collapsing cloud to the dizzying whirl of a neutron star, turning hundreds of times each second. We have watched spinning gas flatten into the disks that give birth to solar systems, seen the planets inherit their rotation and arrange themselves into a single turning plane, and traced how the moon slowly breaks our days while drifting away into a wider orbit. We have stared into the swirling space around black holes, where rotation drags the very fabric of the cosmos along with it, and powers jets that reach across millions of light years. We have measured the rotation of galaxies and found, hidden within their too rapid spin, the fingerprint of dark matter, the invisible majority of the universe. We have followed spin down into the atom, to the intrinsic turning of the particles that make up everything, and back out to the early universe, where the gravitational tugs of the first ripples set the whole cosmos turning, structure by structure, in every direction at once. And we have seen how that randomness of direction is exactly why the universe is so full of spinning things, yet barely spins at all when taken as a whole. Through all of it, one principle held firm. Angular momentum is conserved, born of the symmetry of space itself, passed from body to body, amplified by collapse, redistributed by tides, but never created from nothing and never truly destroyed. The same law that speeds the figure skater as she pulls in her arms shapes the birth of solar systems and the death of massive stars. The same spin that lit our sun turns the ground beneath your feet, gives you your days and nights, and keeps your world circling safely in the warmth of its star. You are a small, thinking part of a turning universe, made of spinning matter, standing on a spinning world, gazing out at a sky full of spinning things, and somehow you have come to understand it. The calcium in your bones and the iron in your blood were forged in stars that spun and died long before our world existed, scattered across space by rotating clouds, gathered again into the spinning disk that became our solar system. You are, quite literally, woven from the turning of the cosmos, a pattern of spinning matter complex enough to look out at the vast rotating universe and ask why it turns at all. The next time you watch the sun sink below the horizon, remember that you are not watching the sun move. You are feeling your own world turn, rotating you gently away from the light, just as it has every evening for billions of years, just as it will for billions more. In that simple, daily turning lies a thread that reaches all the way back to the birth of the universe, and all the way out to the farthest galaxies still wheeling in the dark. Everything spins, and now you know why. If this journey filled you with wonder, be sure to like this video and subscribe for more journeys into the cosmos. And as you go about your day, carried ceaselessly around by a turning world and a turning galaxy, remember that you were never standing still at all. You have always been part of the great, silent dance of the spinning universe.